Hey everyone, my name is Matthew Farrar Beltran, and this is my Lab 2 presentation on projectile motion. So to begin, the purpose of this lab was to track and calculate the motion of an object thrown into projectile motion. As you'll see in the next slide, we have a video of a paper ball just being tossed up in the air. Our object moved in both the x and y direction, or horizontally and vertically. The main principle in our experiment was Newton's second law, which is force equals mass times acceleration. Due to external forces, as we'll see later in the presentation, the net force in the experiment is not zero. Therefore, there is acceleration, there is a change in velocity. We also have our equations in which drag is present. We have our vertical and our horizontal component equations. For the vertical one, the vertical forces that cause, well, obviously an overall force, is gravity and drag. Meanwhile, for horizontal, the force is just drag. And as we'll see later, our object did experience drag force since our object did not move as far or as fast as a simulated object in GlowScript with no drag. All right, so here's the video and our model. So as you can see in the model, we have three different simulations. We have our observed one, which was a tracked through tracker. We have our simulated one represented by the red dots, and that has no drag, and our simulated model with drag with a b-value of 0.5. This is just showing that our paper ball had a lower height than the GlowScript simulation with zero drag, and the closest simulation to our observed motion had a drag value of b equals 0.5. In our experiment, we had a 4.5 gram pepper ball. We just crumpled up a piece of lined paper and just made it into a ball, yeah. And we can assume that our experiment had forces acting on it, meaning that there is an acceleration value and therefore a changing velocity, as I said in the introduction. Our gravitational force is negative 9.8 meters per second squared, and our drag force is, again, represented by the equation listed on the screen. And through our simulations on GlowScript, we found a similar b value of 0.5. Since there is some sort of drag, the paper ball must slow down vertically and horizontally. And as I showed in the model above, our paper ball, the observed one, did have a lower height and lower length than the simulated one with no drag. And we had our initial conditions of x value of 0 meters, y value of 0.297 meters, and the initial x velocity was 0.6934 meters per second, and the initial y velocity was 1.8156 meters per second. So as for our coding, here just listed like all the things we set and changed. I had to set my paper ball mass to account for the 4.5 grams. I set the initial position, velocity, delta t, and the gravity and simulated b values, as I've all mentioned above. In our tracker and just overall the entire experiment, I guess from the hand until the ball landed, that took 0.467 seconds. I included that into our coding, and I also have the F-net vector including gravity and drag force, since those are both forces acting on our paper ball throughout its motion. Ball position, ball velocity was updated for each loop iteration, and I also added the coding for the arrows on the diagram, which you will finally see in the conclusion section. So what does this mean? Our terminal velocity in the y direction could be computed by setting negative b times the y velocity squared equals g. This is because terminal velocity occurs when the drag force is equal to the gravitational force, resulting in a net force of 0. You could also drop a ball from a higher height and let it fall for longer until it reaches its terminal velocity. And for the what if question, imagine if the object was thrown straight up. Yep. The object would take longer to reach the table due to its positive initial velocity. Gravity and air resistance would both act downward until it reached the y value of 0 meters per second. And, the velocity y value, I typed it wrong, of 0 meters per second. And the air resistance would work against gravity as it falls, like in this experiment. This is the conclusion section. As you can see in the picture depicted, my drag force was just like completely off. That is definitely a source of error, but based on the coding that I did, that was the drag value that that best fit my observed motion. I did check it with a few friends, and my coding didn't seem that far off. I'm not entirely sure why my b value was so high, but this is what I found, and definitely a source of error. That could have also just stemmed from either tracker, I guess, inputting my information wrong. I don't think so, because it seemed right. I compared with my group mates. So definitely an error in coding somewhere. Again, though, I did compare and it didn't seem that far off, so I really do not know what happened. Anyways, our object encountered a change in velocity due to gravitational and drag forces, which was air resistance working. And yeah, thank you for your time.